Recording is rolling. Right, so it is Wednesday, August 17th. Remember, I've taken this week to cover a lot of the uh, ground rules for math that you guys are going to be using in this class all throughout the year. A couple days back, we went over some algebra review. Yesterday, I was going to take to do trigonometry and vectors. This ended up taking longer than I thought it would. So one of the pages I gave you guys this page yesterday. It's like has two sides to it. Okay. So actually, today we're just going to spend more time on that, and then all the stuff it's going to do with like scientific method, SI system, dimensional analysis. I'll just say that for tomorrow and see where we're at there. Okay, so let's do a review of some of the notes I gave you guys yesterday. Let me flip the screen over and share my screen here. All right. Okay. Got this tutorial video on scalars and vectors. Okay. So you guys remember in physics there are these two types of quantities. Scalars have a magnitude to them. For example, mass, like how massive is something. Right? Even if you're in deep space, it has the same amount of mass, right? Like amount of matter, amount of inertia. But vectors have a property that scalar quantities do not. What do vectors also have besides magnitude? They also have a what? Some kind of direction. Exactly. Direction. Yeah, which ends up being really important. For example, a force, a velocity, right? Maybe a displacement. Let's look at some examples here. Right, so scrolling through here. So hey, if you do something like this, like 3 meters to the right, has a number, a unit, a direction. If we're talking about a scalar, there's a vector. A vector has to have a direction. Right, so here we go. How about this example? Suppose you walk 3 meters to the right, and then you walk back 2 meters to the left. So from your beginning point to your end point, notice how those are connected tip to tail. You guys remember that from yesterday too? You can geometrically solve like tip to tail vector addition. What is the displacement from beginning to end of your path? What is the displacement? What do you guys think? 3 to the right, 2 to the left? You guys think 1 meter? 1 meter? Good call. It is 1 meter. And then see that light pink arrow? So that's from the tail of the very first one to the tip of the very last one. I know there's only like 2 main vectors there, right? So that pink vector is called the what kind of vector? Starts with an R? Resultant. You guys remember resultant vector, right? Right. So 3 to the right, 2 to the left. Your displacement would be 1 meter to the right. Okay. But you might be interested in something a little bit different, a different property. What if you were in a car driving around and you drive 3 meters to the right, and you turn around and you drive 2 meters to the left? What does your odometer say the distance that the car went is? What distance did the car go? 5 meters. Yeah. Okay, so we got displacement would be 1 meter for that example, but distance is 5 meters. You guys are exactly right. Okay, so that's the difference between a vector and a scalar. Vector, you're about beginning point, end point. It's the difference. A scalar, you're just adding everything up, right? Which is ignoring direction. Right? Right. How about right. Right. Oh, let's go to 2 dimensions. What if you do that? You walk 3 meters to the right and then 4 meters up. Right. Now, from the tail of the first vector to the tip of the last one, so from beginning to end, what is the displacement for that one? Do you guys know some special right triangles? Do you guys know a 3, 4 what triangle? 3, 4, 5. Is that going to be a 3, 4, 5? Yeah, right. There you go. Oh, Pythagorean theorem, right? So Pythagorean theorem could solve like any right triangle, and then if the sides are 3 and 4, it's always going to be 5, right? And then okay, meters in this case, right? Okay, that's your displacement, right? And see how the purple vector is the resultant, right? The path you actually walked was the red arrow followed by the blue, or I should say vector, red vector followed by a blue vector, right? So say you're like walking around a campsite, right? 3 miles east, or 3 meters east, 4 meters north, for example, right? But that purple vector is the resultant vector, right? Now, what distance did you walk? Not 7 meters. Yeah, 7 meters. Yeah, okay. Okay, so displacement's 5 meters, distance is 7 meters. You guys get that? All right. What else we got? Oh, how do you get that angle? That angle. Do you take like something to do with like an inverse trig function? Right?
Like that sine and cosine.
Yeah. Okay. So sine, cosine, tangent. And if you are specifically trying to extract the angle, you have to do the inverse of one of those, right? Right. Now, if you're playing off the two legs, it would be like tangent or inverse tan in this case to get the angle, right? Okay. So remember, sine, cosine, tangent of an angle spits you out a ratio. Inverse sine, inverse, cosine, inverse tan will spit you out an angle. So inverse tan of 4/3 in this case tells you well, how many degrees that is. And that would, I think it comes out to is it 53 degrees for a 3/5 right triangle, right? 53 degrees. How about oh, you could do the red followed by the blue, but does the order matter that you add vectors together? No, you could do going north first followed by east. So you could do the blue followed by the red. And that's what that looks like right there. Do you guys notice that the purple resultant is exactly the same regardless of the order that you put the vectors together? Right? That would also be true. Hey, I know we're doing displacement vectors for this example, but what if it was something like force vectors? If you have an object set in the middle of the table, you put a bunch of forces on. You guys remember the monkeys and the bananas? Remember the hungry monkeys and the bananas? Right? They all pull in different directions, right? You could also do tip to tail vector connection analysis that way, but it wouldn't matter the order of the monkeys that you consider. Oh, change it in here. All right.
Oh, what's going on, Sean?
All right. Yeah. Good. Pick a desk and I'll pitch set here.
Yo, what's
right.
going
Um. So. Okay. Right here. How about if you had lots of vectors? You guys see, here's what's going on here. So you start in the bottom left corner, maybe like the southwest corner, right? We're going to do the blue vector, followed by the red vector, followed by the green vector, followed by the yellow. You guys see that? Like you're walking around a huge campsite, right? And then that purple is still the resultant. So the purple just tells you, well, you started in the bottom left, you ended up in the top right. Right? You guys see that? See how there's that tip-to-tail vector connection? Now, what if you followed each of the blue, red, green, yellow, but just in a different order, right? Would you still end up in the exact same location? Yeah. Yes, you would. Let's watch this animation play out. Oh, look at that. You guys see those vectors slide around? Now it's yellow, green, blue, red. Now notice that the direction of those vectors did not change. They just changed. Right? So when you connect these tip to tail, just the order of connecting them changed, right? Let's see one more animation. Zoop. Oh, look at that. Now it's green, red, blue, yellow, but that purple resultant is still the same, right? So again, same thing if you carry it to a different type of vector, like force vectors, right? You could add the monkey tensions together in any order, and you still get the same result for the banana. Right? Okay, so I think that's let's take away from that one. All right, let's switch back over here. All right. So yesterday, you guys remember getting this page? I did a couple of problems on this side with you guys. If you guys remember, there was it's a vector broken into components, but it sure does look a lot like a right triangle. So all the right triangle geometry, like sine, cosine, tangent, all that, right? Now on the other side is the science portion of this. Well, with science meets the math. So you get to measure, you get to calculate, and so you do these calculations, actually measure up with these measurements. Okay? So let me do, here's what we do. I'm gonna do a couple of examples with you guys on this side. Then I'll do at least one more example on this side, and then I'll give you guys the rest of class time to help each other out, and I'll walk around and help you guys out too. Okay. So it looks like we were starting on Maxwell and then kind of ran out of time at that point. So let me finish this Maxwell triangle, which you may or may not have on your page. All these pages are different. Okay. Now I'm going to do a little trick here. I'm going to extrapolate these legs because the triangles are kind of small compared to the protractor. I mean, this triangle compared to this protractor, see, it's kind of small. So if I extend these legs, that's going to help me measure the angles later. Just like that. Okay. All right. So I need to get angle alpha. Looks like that's as far as I got yesterday. So do that again. Okay. So I'm going to take this node of this protractor. Right, you guys know how to use protractor? I always have students who have never held one of these in their hands before. So it's your lucky day. Get to learn stuff. You take this node, park it right on this corner. I'm trying to measure what's the size of this wedge alpha. Looks like yesterday I got 22 degrees. Let's see if I get that again. Right. Align this with the 0 degrees. And then this should sweep through the angle measure. Now it actually sweeps through two numbers. There's two sets of numbers on the protractor. I see 158 on the outside and I see 22 on the inside. So guys, what does alpha look more like reasonably? 158 or 22? How about 22? Right, it's definitely less than 90 degrees, right? this big old angle here, that's your 158. We don't care about that. We care about the 22 degrees. That's that 22. Okay. If you like, you could actually flip this whole thing upside down. So park the node still on the same corner, zero out the hypotenuse in this case. Okay. And now this leg sweeps it up 22 degrees on the outside, measuring clockwise instead of counterclockwise. Same thing. Right, so I need to measure the other acute angle, beta. Let me try it this way. I'm going to zero out this very short leg. So take this node, park it right on this corner, zero out this very short leg right there. And then this sweeps through 68 degrees. I see 68 degrees. That's the size of this wedge right here, 68 degrees. So 68. Hey, those two, 22 and 68. What do those two angles add up to? 90 degrees. Should alpha and beta always add up to 90 degrees for these right triangles?
Yeah.
Yes, they should. Right. Tell you what, if these angles add up pretty close to 90, if you get like 88 to 92, anywhere in there, in that range, then that's fine enough for this class. Sometimes I'll make a mistake myself in measuring, or sometimes intentionally just make this point. Now, if you were in a math class, these angles have to add up to 90 degrees in a math class. But this class is a science class, which has a little bit different philosophy to it. So in a science class, your own empirical measurements are more important than any textbook theory. So if your two angles happen to add up to like 89 degrees, then that's close enough for this class. And actually that's better than going back and erasing your work and just aligning it with textbook theory. Okay. Right. Do you guys see across the top of this table, it says either measure or calculate? Right. So looks like I need a few more measurements. So now I'm going to break out the ruler and measure the three sides of Maxwell triangle. Let's get side A. This looks like 2. I'll call it 2.7, I guess. 2.7. That would be centimeter. Oh, whoops! I skipped side C. That's good. So 2.7 centimeters. I specified the unit in the table already. They all say centimeters. Right. So I skipped over C. Oops. Let me go back and get C. So Maxwell side C is I'm going to call it 6.9, I think. 6.9 centimeters. And then there's one more measurement I have to get. I'm going to skip a few cells. See, there's one last measurement I need on the triangle, which is side B. Right? So let's go grab side B. This looks like, I'll call that 6.3, 6.3, 6.4, somewhere in there. Maybe I'll call it 6.3 today. Got that. Right. Okay, those are all my measurements. Right? I got the two acute angles. I got the three sides. Right? What's not specified in the table is this right angle, 90 degrees, but let's say that's a given. Okay. Okay. The rest of these cells are all calculations, and it tells you exactly what to do. There's a formula for it. Do you guys? Well, actually, let me save that count for a couple minutes from now. Do you guys see C times sine alpha? Right. Now, guys, if you start with your hypotenuse C, and you multiply that by sine of alpha, this is in your notes from yesterday, that refers to which side? B. You guys remember sine of alpha is defined as B over C. Therefore, C times sine alpha spits out B. Right? Okay, so this should refer to side B. Let's see if it does. Calculator, take my C, which was measured as 6.9 centimeters, multiply by sine of alpha was 22 degrees. Oh, don't mix up alpha and A. Those are completely different concepts, right? Different units. But alpha is 22 degrees on Maxwell. So I'm getting 2.58. I'm going to round that to like 2.6. Right, 2.58 is about 2.6. Right. What does the next column say? The next column says C times cosine of beta. Right. Now, if you start with your hypotenuse C and you multiply by cosine of beta, hey, was cosine something to do with adjacent hypotenuse relationship? So if you start with the hypotenuse, multiply by cosine of beta, isn't that going to also flip over to the side A? So that's a different perspective of how you can get side A. Let's see if this works. What is 6.9 centimeters times cosine of 68 degrees? That's also 2.58. I'll round that to like 2.6. Okay. How about, what's this? Square root of C squared minus B squared? Where's that coming from? What's that a reference to? What formula? Maybe I should say what theorem. Here, guys, on this Maxwell triangle, is a squared plus b squared equal to c squared? So a squared plus b squared equals c squared. You guys remember that from your notes yesterday, or probably from elementary school. Suppose I was to solve for this a. I'm going to do this in terms of variables, which I probably won't do very often in this class, but maybe every once in a while, including right now. Right. I'm just going to do some algebra. Can I subtract this b squared over and say a squared is equal to c squared minus b squared? Can I do that? Right. And then if I'm solving for a, what's the last algebra step? Do what to both sides? Square root. Right. Hey, square root of c squared minus b squared. That's what this says. So this is a way to calculate side A going through the Pythagorean theorem. Let's try this out. Let's see if this works. What's the square root of c squared, 6.9 squared, minus b squared? Now b is right here, 6.3 squared, right? And that is 2.81. Maybe I'll call it 2.8. 2.81. Right? Ooh, do you guys see a very dark rectangle around these four columns? You guys see that? That's because within any row, those four cells are all referring to the same side of the triangle. And look at those numbers, 2.7, 2.6, 2.6, 2.8. They're all extremely close to each other because they're all referring to the same side, this side. Just you get there from different perspectives, okay? Let's finish off this row. So c times sine beta. So these are just calculations at this point. So all I need is this calculator. C, 6.9 centimeters, times sine, and beta was 68 degrees. I'm getting 6.397, or so I'll call it 6.4 or 6.4. Okay. Next one, c times cosine of alpha. That's 6.9 times cosine of, now my alpha was 22 degrees. Remember, alpha and a are two totally different concepts, so don't mix those up. 6.397. Okay, so it's also 6.4. Okay. And the last cell says square root of c squared minus a squared. Do you guys see that it's going to be like same concept here, only if you solve for b, you get something like this. B equals the square root of c squared minus a squared. You guys see that you could have gone that way, right? Solve for b. That's exactly what this means. So let's do the square root of 6.9 squared minus 2.7 squared. And that is 6.3498. I'll round it. So 6.35 rounds. I've been doing 2 digits. I should have been keeping another digit all along, but okay. But look at this. Do you guys see how these four numbers are extremely close to each other? 6.3, 6.4, right? Because they all refer to the side, just from different perspectives. Okay. You guys good so far? Okay. Let's pick another triangle. How about this curry triangle? Now this curry triangle is pretty small, so notice it's smaller than my protractor. So to help myself out a bit, I'm going to extrapolate these legs. So all right, the first two values I have to get are alpha and beta. So protractor, measure alpha. Right, so what's the size of this wedge right here? There's 2 ways to do it. You could park the protractor this way, zero out this leg, and go counterclockwise, or you could still park the node on the corner, but zero out the hypotenuse instead, and see where it is the leg cross through. And this looks like, I'll call it 52 degrees. I think I'll call it 52 degrees. 52 degrees. Okay. How about beta? How about that angle beta? So take this node, park it right on this corner, zero out the leg, and the hypotenuse crosses through. That looks like 38. Looks like 38 degrees. Oh, 52 and 38. What do those add up to? 90 degrees. You see that? Again, if your 2 angles add up to like 89, that's good enough for this class. 91 is good enough. Okay. When I say this class, I mean science as opposed to math, right? math, they better add up to 90 degrees. They just happen to today for this example. Right, so side C, what is the side C? I think I'll call it 5.4 maybe, 5.4 centimeters. I think last class I also used this triangle and got like 5.5, so trying to measure it, I guess I'm a little different. Right, what's the side A? I think I'm gonna call it 4.3 centimeters. And then skip a few cells because there's one more measurement I have to grab, so I'll just grab this real fast. Side B is like 3.4, looks like 3.4 centimeters. Okay, so now I've got all my measurements, okay? And these last 6 cells are all calculations. So C times sine alpha, and remember, it's gonna follow the same pattern as did for the last one. You guys see a stark rectangle? That means these 4 cells should all refer to side A. We got the direct measurement and 3 calculations that should also get us there. So do C times sine alpha. C times sine of alpha, 5.4 centimeters times sine of 52 degrees. Calculator says 4.255, going to round that to like 4.26. I really should have kept an extra digit just for funsies, so I'll go and do that here. Oh, yeah, go ahead.
What are these extra calculations you can do?
All these calculations now you do? Right, because I want you guys to see that you can, if you can't directly measure something, that you can at least calculate it. Here, I'll give you a real world example. And we'll be using this in physics all over the place, but just to pick one for fun. Suppose you're looking down on the world and you see like a hill right here. There's this big old hill. Okay. And you're on an engineering team and you have to run a railroad track through the hill. We're going to build a tunnel. We're going to tunnel through this hill, right? Okay. And you have to figure out, well, how long is the tunnel going to be? Because you have to know the length of the tunnel so that you can figure out how much dirt you have to extract, and you have to plan for like how long you have to rent the machinery, right? It's a whole planning process. But I mean, there's a hill in the way. So how do you get that length? Well, you could do some surveying. You could say, well, I know from this point to this point, there's like it could be it could be like a triangle. Do some trigonometry. You can say, well, I know that this length here from this, like the change in the east coordinate is like that far, and I know that the change in the y coordinate is like that far. So then I could do, hey, Pythagorean theorem, and I could calculate, right, how much dirt we have to extract, right? Like you can't directly measure it, right, until you're like in the middle of the process. Right? But you can calculate it ahead of time because you say, well, I know it's this far east and it's this far north, and I could do Pythagorean theorem. Right? Something like that, right? So yes, sometimes, but depending on the information you have, right, and on the other side of this paper, which I'll do some examples for you guys too, you could have like any given set of information and have to figure out what anything else is. So the point of this is I want you to see that the calculations actually do align with the direct measurements, right? So the math and the science all come together. Okay? Right. 4.26, that does round to 4.3. So we're good on that front. The next one, what is C times cosine beta? So 5.4 times cosine of, now my beta was 38 degrees, also 4.26. By the way, if your angles, if alpha, beta do add up to exactly 90 degrees, which both mine here do happen to, then these two middle, so like, here's what I'm trying to say. Let me put this in more, if alpha and beta add up to 90 degrees exactly, then, if then statement, then sine of alpha and cosine beta will be the exact same thing. In fact, you might remember that from a math class. Right? I can also say this. Cosine of alpha and sine of beta would be the same thing. Okay. That's if they add up to 90 degrees. Now, if they add up to 89 degrees, then it should be pretty close to that, but it might be off a little bit. Okay. And last way to get to side A would be to Pythagorean theorem, but rearranged. Okay. So square root of c squared minus b squared. So 5.4 squared minus 3.4 squared is 5.075, maybe it's like 5.08 rounds, like 5.1. Okay. Now that one's kind of off a little bit, isn't it? because measure value is 4.3, the sine and cosine stuff agreed with that. But the Pythagorean theorem, it's off a little bit. Not enough that I would think I typed something wrong, but having taught this class a number of years, if there's one measurement or one calculation that ends up being off more than the other ones, it actually does end up being Pythagorean theorem. That's usually like the least reliable way to get there. Right. And then how about these last three? Now, these last three cells should land pretty close to 3.4 centimeters. Let's see if they do. So c times sine beta, 5.4 times sine of 38 degrees. Because if you start with your hypotenuse and multiply by sine of beta, see how sine of beta is going to flip from your hypotenuse to opposite of beta, which is side b, which here's your side b. Let's see how close to 3.4 centimeters this is. 3.32, 3.32. That's extremely close to 3.4. I'll take it. Next one, see cosine alpha. 5.4 times cosine alpha was 52 degrees. That's also 3.32. Just like I told you guys, these two have to be the same number because my alpha beta do add up to 90 degrees. Okay. 52 plus 38 is 90 degrees. And final one for the Curry triangle, square root of c squared minus a squared, because remember, c squared minus a squared, square root of that should give you side b. It starts from this Pythagorean theorem that you guys have done since elementary school. So square root of 5.4 squared minus 4.3 squared. Remember, your alpha and your a are two different concepts, so don't mix those up. That is 3.266. I'll call it 3.27. Okay. 3.27 rounds to 3.3 is really close to 3.4, which was my measured value, so I'll take it again. All right, any questions so far? You guys doing all right? All right, so done a couple of those examples with the guys. Flip this page over. I did a couple of these yesterday with you, so I'll do at least one more. How about number, let's do number 6. Number 6. Okay. Now, number 6, I gave you one of the angles and also one of the legs, side x. And also the fact that it's a right triangle, these are all right triangles, but that's it. Can you figure out everything else about the triangle? You work your way around this triangle. Who can tell me what my alpha value is going to be? If beta is 70 degrees, what does alpha have to be? 20. How do you know it's 20 degrees? Yeah, these add up to 90 degrees, right? Okay. And again, ideally, you're on a right triangle, your two acute angles should add up to 90 degrees. Okay. And since this is like a pure math side of the paper, then they will add up to 90 degrees. Okay. Right. So we've got one of the legs of the triangle, side x. Right. There is enough info around. If you know how the triangle is proportioned and at this point how big it is, you could figure out what is side y and side c. Okay, these are all in kilometers. So let's figure this out. Okay. And there's more than one way to get to the correct answer. So I will do one way in these notes. Okay. Actually, I should have dashed these components just like the model is showing. So, because one of the most important aspects of trigonometry and physics, like the application, is vector components. So you might say, okay, I walked some distance z northeast. So I started on the southwest corner and I walked northeast. How far did I walk? We don't actually know yet. But I do know that I changed my east coordinate by 22 kilometers. I'm like 22 kilometers east overall. I don't know exactly how far north I went or how far I walked in total. I do know that this is a 20-degree angle, and I know that this is a 70-degree angle, right? If I'm like getting my bearing. Okay. And see, this side is 22 kilometers, right? So how far north did I walk? What is y? And how far total did I walk? Which is side z, right? Okay, so again, there's more than one way to approach this, but I have one of the legs and I have the angles. So how about this? If I'm playing off the 20-degree angle and I want to get side z, so 20 degrees and I want to get the hypotenuse, what relationship would this be? Sine, cosine, or tangent? got the adjacent leg and the hypotenuse, SOHCAHTOA, that's got to be what? Cosine. Yeah, cosine. Right. So I do know that cosine of the 20-degree angle is the ratio 22 kilometers divided by side z that we're solving for, right? SOHCAHTOA, right, from your notes yesterday. Right. Okay. Hey, let's just do a couple of algebra steps and solve for z. Should I cross multiply up z? Z times cosine of 20 degrees comes out to 22 kilometers. And what's the last algebra step to isolate z? Z equals what? Okay, take the cosine and divide it down. Take 22 kilometers and divide by cosine of 20 degrees, right? Okay. There you go. These three lines all say the same thing, just it's rearranged, but now it's to solve for z. Okay. Let's see what that is. 22 divided by cosine 20. But before I hit enter on the calculator, let's get an estimate of what looks like it might make sense. 20 degrees, that's kind of a skinny angle, right? You guys think this hypotenuse is going to be what, more than or less than 22 kilometers? It's got to be more, right? Hypotenuse is always alongside, but probably not very much more because 20 degrees is a pretty skinny angle. I'm going to guess 30. If I get anything in the ballpark of about 30 kilometers, let's see what it actually is. Oh, not even that much. It's 23.4. Actually, I can believe that too, because just how angles work. Right? So 23.4 kilometers. Yeah, actually, it's barely anything more. But it's a real skinny angle. 20 degrees this way. Right. Last thing we got to get is side y. Right now we got some options. So I'll do it two ways, although there's definitely more ways than that to do it. But I'll show you guys 2 ways so that no matter how you do it, you always get the same answer. If I'm still playing off 20-degree angle and the 22 kilometers, because the 2 legs of a triangle have what relationship with each other, sine, cosine, or tangent? The 2 legs are always what? Tangent, right? So I can go tangent of 20 degrees is opposite over adjacent, right? TOA, as in SOHCAHTOA. Right? So tangent of 20 degrees equals side y that we're solving for divided by 22 kilometers. Okay? Is that right? SOHCAHTOA, let me write down that acronym. Sine is equal to opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. SOHCAHTOA. Okay. So tangent of 20 degrees is opposite over adjacent. Okay. Now there's only one algebra step to get to the answer. Just cross multiply up the 22 kilometers. So y equals 22 kilometers multiplied by tangent of 20 degrees. Wouldn't that be true? Not the only way to get it. It's one way to get it. 22 tan 20. 8 on the nose. 8.0, well, 8.01. It's pretty close. Kilometers. 8.01 kilometers is equal to y. 8.01. Or maybe just call it 8.0, right? Now, I said that wasn't the only way to get that. So let me prove to you guys that had you used a different method, you would also get the same answer. Okay. Hey, could you have used Pythagorean theorem if you wanted to? Pythagorean theorem? I've got the triangle here. Okay. Now, at this point, you would have known, let's say you solved for z already, and you already got this was 23.4 kilometers, right? Which is like the total distance you walked. Okay. Can you figure out what was the change in your like your latitude, right? How far north did you end up going exactly? Okay. So could I say that x squared plus y squared would have been z squared? Okay. And let's say we're solving for y, right? No, you guys know what the answer is already because we used this method and got 8 kilometers. But I want to show you guys that had you used this method instead, you would still get the same thing. Okay. So I got 22 kilometers plus y squared, right? Plus y squared equals 23.4 kilometers being squared. Okay. I'm going to plug in what is 22 squared. It's 484. So 484 square kilometers plus y squared is equal to 4 squared, 547.56 square kilometers. Okay. So now we're back to algebra, which we did back on Monday, right? So we need to solve for y. We can do this all in 2 algebra steps from this point. I'm going to take the 484, subtract it over. Break out the peak ink. Minus 484 minus 484. It's going to be y squared is equal to, so that minus 484 is 63.56 square kilometers. Okay. And what's the very last algebra step? Do what to both sides? Square root. Square root. Okay, we'll do this in purple ink. Square root. Square root. So then I'm getting y equals. Did I tell you guys a fancy way to do square root with a power? Square root, same thing as a power, or what? Half, power half. Here, you guys want to see a real fast trick? 63.56, right? Power 1/2. Boom. 7.97 kilometers, because the unit also gets the square root, right? Hey, and using the other method, we got 8.0, well, 8.01. Right. Now, this 23.4 is rounded a little bit. That's why it's not exactly the same, but I mean, 8.01, 7.97, that's the same distance, right? Is that? All right. Who's got any questions so far? Any questions so far? Okay. All right. So here's your assignment. Assignment. Okay. So choose any 5 on the trig puzzle side, which is the side that you're looking at right now, on trigonometry puzzles. Okay. So there are 10 altogether, but just pick any 5. Actually, we did 3 already, so boom, boom, boom. Okay. And then on the lab side, where we already did 2 of those, go ahead and finish the other 3. So finish all 5 on the trig lab side. Trigonometry lab side. Okay. Okay. So you're doing 5 from each side, right? All 5 on the lab side where you actually broke out the protractor, got some measurements, and also any 5 of the 10 on the pure math side. Okay. Right. And I will walk around, help you guys out, answer any questions you have. Let's have this. If you finish by the end of today, you guys see this gray tray right here? You guys see gray tray? Right, if you finish by the end of today, you can just pop that in the gray tray. Otherwise, let's have this due Friday. Okay. All right, and end.